Okay, hi everybody. Um, Philip, can you hear me? Just checking.
Yep, I can hear you.
Great, thanks. Sorry, I just had to switch headphones, so just making sure it works. All right, well, welcome back. Welcome everybody who's jumping in. Great to have you here for the second segment of the second day of the 2025 ISS Research and Development Conference virtual technical sessions. Really great to have you here. Have you all here. We just had a great session on workforce development and STEM. And now we're going to get into in-space production and applications. And then after this, starting at 3:30 today, we'll have commercial and non-governmental use. And then we'll have three more sessions tomorrow. So we're rolling right along. It's been some really good presentations, really good Q&A. We definitely encourage our attendees to join in on the Q&A, submit via the tool. But I don't want to steal too much thunder from Philip here. So I'm going to turn it over to him. And please welcome Philip Irace. He is Program Director at the ISS National Labs. Take it away.
Yeah, thank you, Jim. Good afternoon, everyone, and welcome to our second session of the day, which, as Jim just said, will be focused on in-space production applications, or INSPA, as you'll hear. As Jim said, my name is Phil Iris. I'm a Science Program Director with the International Space Station National Lab. I'm going to be your chair for the session. So most of you probably already know this, but for our session today, we'll present the 5-minute executive summary video. Then we'll have that author come on screen for a 5-minute live Q&A session. We'll then move on to the next presentation and author, and so on. Webinar attendees will not be able to come on screen, so please use the Zoom Q&A tool to submit any questions you might have. And please don't be shy. We want to have a nice, fruitful discussion with our authors. If we have any time left at the end of the session, we can address any additional questions that might come along the way. And lastly, these sessions are going to be recorded, and they'll be made available on our website as soon as possible. If you want to see the full 20-minute presentation, please visit the online program and open that file up. So without further ado, we'll go ahead and get started with our first presentation, which is going to be Diamond Films for Quantum Computing and Electronic Applications by Stephen Meckler, Vice President of Commercialization with Single Crystal Diamond.
Hi, my name is Steve Meckler. I'm here with Single Crystal Diamond to present the executive summary of our presentation, Diamond Films for Quantum Computing and Electronic Applications. Here at Single Crystal Diamond, we're interested in diamond as far more than just a gemstone. It's an advanced material for next-generation applications in things like semiconductors and quantum. This is because diamond has a lot of really exciting inherent properties. They're not all listed here, but a few representative ones are its very high ultra-wide band gap, its high thermal conductivity, one of the highest of any known bulk materials, and the formation of something known as a nitrogen vacancy center, which is where one of the carbons in the lattice is replaced by a nitrogen, and the site next to it is vacant. And this nitrogen vacancy center is a quantum system that can be used for sensing and quantum computation. Because of this, lab-grown diamond has applications in electric vehicles, navigation in GPS-denied areas, in aerospace and defense, biomedical sensors, as well as smart grids and quantum computers. Despite the promise diamond has for so many of these applications, it hasn't yet been widely adopted by industry. This is primarily due to issues with supply and the manufacturing of large, high-quality diamond. Most of the existing products on the market today exhibit small size, high defect concentration, poor control over those nitrogen vacancy centers, polycrystallinity, as well as things like low supply and high cost. This is where single crystal diamond comes in. The SCD team is comprised of experts who've been working at the forefront of plasma-enhanced chemical vapor deposition, or PECVD, of commercial lab-grown diamonds since the onset of the field in the early 2000s. During the intervening time, they've been able to pull together a lot of know-how and intellectual property that allows us to economically produce larger and higher quality single crystals. We were awarded through the NASA In-Space Production Applications, or INSPA program, funding to look at further improving the growth of diamond using the space environment. There are two aspects of the space environment we're looking to take advantage of to grow higher quality diamond crystals. The first is microgravity. There's good indication from a small amount of prior work in the literature as well as simulation that the plasma in which the diamond is grown will be more uniform without buoyancy-driven convective flows. There's also space vacuum itself. High quality vacuum is very important in the production of semiconductor materials, and using space vacuum we hope will reduce the amount of nitrogen impurities in the final diamond. So bringing all that together with the other IP and know-how that single crystal diamond brings to the table, we want to go from the old paradigm of limited lateral growth, low nitrogen vacancy center concentration, high contamination, and polycrystallinity at the edges, which can lead to cracking of the diamond, to a new regime where our space diamond will have single crystals without strain, wider lateral growth, controlled nitrogen vacancy concentration, and crack-free crystals. We believe that the type of crystal we'll be able to make in space will be superior to what is possible to be made on the ground. A critical aspect of our production process is our ability to produce many devices from each diamond grown in space. After the diamond is returned to our terrestrial labs, we can use a liftoff process illustrated here to selectively remove active layers of high-quality space-grown diamond around 0.6 microns in thickness for use in devices. Because the diamonds grown in space coming back to our labs will be about 100 microns or greater in thickness, it means that we can make more than 100 devices from each of the in-space diamonds we grow. This is critical to achieving high returns on our in-space production activities. This slide shows a more long-term vision of our in-space production capabilities and how they can increase as the in-space infrastructure also becomes more capable. This plan was developed in collaboration with our partners on the INSPA award at Axiom Space. Phase 1 is the INSPA work we're currently executing, and we'll be able to create 9 wafers, each of which will produce over 100 devices, meaning we can expect over 1,000 devices for integration, testing, and commercialization in the next few years. As Axiom Station comes online, we'll increase the size of the reactor along with the production cadence. Our pilot scale reactor will be able to produce over 50 wafers per year with a larger 10 by 10 millimeter size, allowing us to more reliably feed the market with high quality diamond. Finally, we've projected what a full manufacturing scale process in microgravity will be able to achieve. We see the potential to access more than $200 million of annual revenue once this manufacturing scale is achieved. We'd like to thank the NASA INSPA program for their support of this work, as well as our partners at Axiom Space. We'd also like to thank our performance testing partners at Quantum Catalyzer, Los Alamos National Laboratory, NIST, and the Lawrence Livermore National Laboratory. If you're interested in learning more, please check out the full-length presentation, and we look forward to getting your questions at the Q&A portion of the virtual conference. Thank you.
Thanks, Steve. Great presentation. We'll already have one question coming in, so we'll just go ahead and kick it off. What space duration is needed for the diamond crystals?
That's a great question. So the growth takes place over a matter of hours to a few days. So pretty reasonable for the resource utilization on the ISS. And as I mentioned in the presentation, one of the really exciting aspects of this technology is each of those growths gives us one of those space crystals, which using our liftoff process can turn into over 100 devices. So just to kind of put the context of the scale of what that time in space is giving us in terms of commercialization.
Okay, and that's for that specific height of crystal, right? If you went higher, it'd be longer, and the opposite. Okay.
Yeah.
A lot of excitement in the Q&A. How soon are you planning to fly this experiment?
So we're looking to fly the reactor sometime, mid next year, Q2, Q3, I think is the current timeline. We would be doing our first few growths in our first mission. And one of the exciting things is because the reactor can stay there, we're able to sort of send some of the starting materials up and do subsequent missions without requiring additional flights. And so that's something that we'll be looking over the next couple of years to do 3 missions as part of this effort.
Okay. Do you mind expanding a little bit on what platform you'll be using on the ISS? I know you have your reactor, but will it be inside or outside? And then
yeah, it's a great question. Sorry, go ahead.
I was just gonna say, and then after that, what kind of doors do you expect your experiment to unlock, right? Assuming everything goes as planned.
Yeah. So some great questions there. So we're looking at an internal payload right now. So it'll be installed in the express rack. It'll take up 2 locker slots, one for avionics and one for the reactor itself. In terms of what we're unlocking, looking at the future, the internal capabilities, of course, we'd be able to make these diamonds. There's sort of a couple different directions I can take this in. From a market standpoint, I think there are a lot of places where Diamond can open up new capabilities in quantum and high power electronics, but where the supply chain just doesn't really support those markets yet. And so we see sort of a flywheel opening up where we're able to make larger, higher quality crystals. This opens up a whole new set of applications, which increases the demand, and we're able to increase our production to meet that demand. From a technical standpoint, something else that I want to point out is that moving forward, I mentioned space vacuum as something that's very exciting. We, have talked about internally external payloads as another option. There's of course additional layers of complexity there. There was ways that we could make use of some of the free flying platforms to take advantage of that as well. So these are all things that we're thinking about moving forward.
Okay. Next question is, could you have the same benefit for making carbon nanotubes or graphene the way you're doing diamonds?
That's an interesting question, and sort of lacking a lot of expertise in those particular materials myself. I'd have to defer. That being said, the reactor we're building could potentially be used for other experiments. So if anyone here is working on those materials, thinks there could be an area to collaborate in the future, please don't hesitate to reach out. I'd be interested in having those conversations.
Okay. Does your process require a lot of power?
Yeah, so that's a great question. We moving forward, I think, as we look to move to the pilot and the full scale production, one of the things I tell folks who are working on the infrastructure side of in-space manufacturing is the more power you can give us, the happier we're going to be. And the more we're going to be able to do, the larger the crystals and the higher the quality. We are able to scale our process. And so, we're working very closely with the ISS program office to make sure that our power requirements are in line with what they're able to give us. But as we look to really scaling this out, the more power we have, like I said, the greater our capabilities are going to be. So this is sort of my pitch. I took go into in the 20-minute version, I go into this in a little bit more detail. But solar panels, radiators, whatever your system, your whole power thermal system looks like, is going to be pretty key to unlocking the full potential of this, at least this corner of the in-space manufacturing market, from my opinion.
Okay, great. I think that's about all the time we have for this Q&A. So go check out Steve's full presentation. It's on the website where you registered. There's a full agenda available with the presentations, and I imagine Steve's email is probably in his presentation if you'd like to contact him.
Yeah, look forward to talking to you all. Thank you so much.
And we'll leave Steve in the in as a panelist so he can keep typing some answers into the chat if you want to, Steve.
All right, thank you.
All right, thanks.
Good to see you.
Go ahead, Phil.
All right, our next presenter will be Felix Steiner, Head of Business Development for New Space at URI. And his talk is titled "The Post-ISS Era Begins Today, URI Science Taxi on Haven 1." And I might have underplayed that. There's an exclamation point, and I don't know if I put it out there enough, but welcome, Felix.
And we'll go with his presentation.
Hi everyone, my name is Felix. I'm from URI. I'm the head of business development New Space, and I'm going to tell you today a little bit more about us, what we're doing and what we will do in the future in terms of space biotech and launching your experiments to the commercial LEO destination Haven 1 within our science taxi. So with that, the post-ISS era begins today. URI, who we are. So we are a German, Luxembourg and US based space biotech company, payload service provider to the ISS at the moment. And in future on, we are also launching your experiments to the commercial LEO destination Haven 1. So what we're doing, so we are a team of about 35 people right now, having more than 100 years of experience in payload services, more than 60 customers on the globe, and also having more than 106 labs launched to the ISS and to low Earth orbit so far. What is our core business? So on the one hand, we have, as I said, our lab as a service, which is our payload service, and also our science as a service, which you can see as a commercial research organization. And therefore, we are having a 3D bioprinter. We are having our science taxi biospin, which is a space incubator. We are having our random positioning machine, which is a microgravity simulator, well known also in the US. We have several customers there in the university, but also at the KSC, and also having the Science Taxi Haven 1, as you see it in the bottom. But on the other side, we also work on our own bioassets in the background. So we are having quite a good relationship to the globe, having, as I said, many customers. You see it on our map where the customers are located. So it's global.
Sorry about that, everybody. It seems like the recording is only on the first slide, so maybe we'll just go back to the first slide, play the recording, and then when that's finished, we will click through the slides. Felix, do you want to just talk to your slides really quickly as we go through? You can come on and do that.
I can do this. Yes, sorry
Okay.
for this bad mistake. So yeah, I will do it real quick. So on this slide, you just see like the founders of Yuri. Have more than 100 years of experience and launched more than 160 labs to the ISS. And right now our science taxis on the ISS went up with NG23.
Slide.
Here on the left side, you see our current facilities we are having and we are going to build. So Science Taxi Bioforge is the bioprinter on the top left. On the top right, it's Science Taxi Biospin. This is our incubator currently on the ISS. On the bottom, you see on the left the random positioning machine. This is our microgravity simulator we are offering also globally. And on the bottom right, it's Science Taxi Haven 1, which we are launching with VAST next year on Haven 1. And then having 4 missions. Please, next one. Just like where our customers are coming from. And our last launch was NG23, and we're based in Germany, Luxembourg, and the US, as you can see. Just a few images. Thanks, credits to NASA for the images. Our last mission, we went up to the Sable 1 facility on the ISS on a SpaceX 32 launch, and we launched for a commercial customer for nutrition experiments. There you see our sign shells. And yeah, so last year we signed a binding contract with VAST, launching our Science Taxi on Haven 1, and we are now opening up space beyond the ISS and starting some commercial new space actions in low Earth orbit. And there you just see the Science Taxi Haven 1 facility incubator. Works between 15 to 37 degrees, having slots for at least 24 experiments, works autonomously. And here you just have an overview of our missions with VAST. So first mission will be in June 2026, which is already sold. We're talking also about mission 2, 3, and 4 with international space agencies, which are highly interested to have some capabilities and first missions outside of the ISS. Thank you very much, and sorry for the bad mistake. Happy to hear your questions. And as Jim said, all of the presentations are online. Just reach out.
All right, great. Thank you, Felix. It's a nice talk. I guess I'll kick it off with the first question. So you said you're launching on Haven 1. So do you have plans to launch continuously on each ride to Haven 1?
Yeah, so we signed contract with VAST for all 4 Haven 1 missions, where Dragon Capsule will dock for 14 days to Haven 1. And on each mission, we are flying up the sign shells, so our small bioreactors with the fluidics, which we are building by ourselves and are highly modular. So this will be launched, and every mission, which is, I think, every 6 months. So mission 1, then 6 months like pause, and then we have mission 2, and on each mission you can launch up to 24 sign shells.
Okay, great. I'll take 1 or 2 from the chat, the Q&A. Will Haven 1 accommodate live loads, for example, fish or other animal species?
We can accommodate that. So we can make it possible within our sign shells. We would load it yeah, on ground. Depends what temperature you need, but we can upload temperature controlled. We can have like fluidic exchanges there. So yeah, live animals can be launched if requested.
One more quick one. Could the experiments run on Haven 1 when there's no crew to run them?
Whoa, did
So
not discuss this with
yeah,
the VAS guys yet,
during the
but
unfree period.
could be possible on long-term mission. But this needs to be further discussed. Also depends on how much media do you need. So we can launch up to 2U payloads. One 2U box would fit in. Depends on the media amount and if we have like power during the transition between the two missions. But reach out and we can discuss it.
Okay, great. Thank you, Felix. And as Felix said, reach out and ask him any questions you might have. And with that, we'll go ahead and move on to the next talk. We have Professor Nirmala Kandadai from Oregon State University, whose presentation is titled Laser Sintering of Printed Electronics for In-Space Manufacturing. So we'll go ahead and kick it off with the video.
Good morning, everybody. I'm going to be talking about laser sintering of printed electronics for in-space manufacturing. This is an executive summary of the work that we have done for in-space manufacturing of electronics and the applications of laser sintering. So our main motivation for our work is printing of electronics is valuable for space, not only because of the fact that they are conformal, they can be flexible, but also because they are cheap and they can replace devices quite easily. Specifically, if we are trying to look into next generation of electronics, where we are looking at flexible cell phones, these devices have various applications, and particularly in space where there is a need for cheap replacement of electronics quite urgently, this becomes really useful. So in our talk, I will be focusing on two applications. One is on-demand manufacturing of electronics, which is usage of this technology in space for space, and then our work with semiconductors for in-space manufacturing, which to be produced for printed electronics to be produced on the International Space Station or low Earth orbitals, which is in-space manufacturing for Earth and commercial applications here. So in the work that we did for on-demand manufacturing of electronics, we studied the most suitable laser system that we could provide for a printer that could be in space. So in this talk, I will be presenting our results on how we concluded and down selected the laser that could be integrated for ODME, on-demand manufacturing of electronics. And then we also showcased that how this system that we chose could be applicable for a specific application where we were looking at improvement of creation of conductivity sensors for water purification applications in space. So this is an important application where wastewater is converted to potable drinking waters for astronauts. The second application that we will be talking about is space-enabled devices and semiconductors. This is our applications for in-space manufacturing for Earth application. We utilized a technique called as EHD printing as our printing methodology for this application. This was in this project we will showcase how not only we down selected the laser and showed laser to be very efficient, we actually tested it on how this works under microgravity and zero gravity by using zero G's flight campaign where we actually integrated a laser system with a printer and then flew it on a zero gravity plane and then tested it under lunar gravity and zero gravity. We'll also show that our laser sintering, while this useful technique and is applicable and works really well under microgravity, will also show that how microgravity itself allows for improvement in the performance of laser sintering and for improvement in printed electronics per se. So this is the executive summary for the work that we'll be presenting. Thank you.
All right. Thank you, Professor Candidate, for your presentation.
I apologize. I had a cold when I recorded it. I did not realize how quiet it sounded.
No, that's okay. The full presentation again is in the agenda online if you want to go check that out. So I'll kick it off with a question before they start popping up in the Q&A. So as you were developing your low gravity experiment, what kind of challenges did you face? I mean, I can see a lot of things with like fluid handling and deposition, obviously being much different.
So we actually saw an improvement. We thought it would be much harder. Biggest thing was just movement and making sure everything is set, and then they can move well inside microgravity. But when we were doing printed electronics, we were trying to, so our application was to do printed electronics. If people couldn't hear it, we were trying to create electronics that can be generated in space and then used on Earth. And printing seems to be the technique, and laser sintering was the technique that we tried to use it. Actually, both the technologies of printing and laser sintering showed improvement, marked improvement under microgravity, which was surprising. We thought it would be worse. So, for instance, we had better resolution printing because there was no gravity, so you did not have lateral flow of the inks, and we were getting improved resolutions. And then also with laser sintering, we saw higher heat deposition under microgravity than we did under on Earth. So it actually showed a significant improvement. So you had better improvement in lunar gravity and then much better improvement under zero gravity. So kind of showing that this is a technology that would be used for in-space manufacturing.
Okay. So we got some questions popping up in the Q&A. I think you answered the first one of whether it can be used in reduced gravity environments such as the moon and Mars, because I heard you mention lunar. Yeah, feel free if you want to expand on that.
Yeah, so they would be improved in. So we had two applications. One, we were working on like on-demand manufacturing of electronics, which was for to see if we can do this on. Idea was for it to be going on the Mars mission before budgetary constraints. Yes, absolutely. It will be improved compared to what we see in Earth. So that means if I'm using a 6-watt laser on Earth, I would need to use only 5 watts on Mars and probably 4 watts on microgravity. So yeah, so it shows that there is an improvement. We are hoping that this would help. So the biggest challenge with printed electronics. So I'll give you the positives and negatives of printed electronics. The positive is it's really cheap. You can use it on flexible substrates, conformal substrates. The negatives are when you compare it with state-of-the-art semiconductor manufacturing, we don't have the resolution. What we observed that was when we go under microgravity and lunar gravity, we improve resolution significantly. So, which means that we can create better circuits that are conformal. So, kind of, it is kind of Star Trekky, but, imagining that you have a wristband with an electronics which pops up and makes a phone, all of those things can be done using this kind of technology rather than doing this on like a rigid substrate. So I do see a huge improvement when we go up into reduced gravity per se.
Okay, and I think you almost hit on this next question, expanding on the difference in sintering results between gravity, microgravity, and 1G. So can you maybe
Yeah,
quantify? Good.
expand it a little bit more. So what we observed was that we saw better, so same power when we used it for microgravity um, uh, on Earth and then lunar gravity, what we saw was we saw more fusion. So again, it just means that we need lower powers to achieve the same technology. Now, we only did silver as our first experiment. We believe this will we have other materials where we actually lasers can be used to create crystalline structures, so when you hit a nanoparticles, they are disparate particles, and then you're coagulating to make more kind of films. So we believe that this is all going to get improved with microgravity per se, that there is going to be an improvement in every technological aspect of it, just because there is improved heat flow. And also because of, so we don't quite understand. We just looked at convection, no convection for our modeling perspective, but I think there are multiple other aspects that play into role when we are doing under microgravity. I think we'll have better crystalline growth, better sintering results, more uniform films. So I do believe that this is going to be a better technology under microgravity than it is on Earth.
Okay, great. Thank you. With that, I think we're gonna have to move on. You do have a few more questions in the Q&A, but feel free to continue answering those in the chat.
Sounds good.
Thank you very much for your presentation, and we'll go ahead and move on to the next one. Do you have anything, Jim?
Professor, exactly. Feel free to answer in the chat and we'll get to your questions and on to the next one.
Excellent. Next, we have Lynn Harper, Strategy Lead for NASA In-Space Production Applications Portfolio with the NASA Ames Research Center. And her talk is going to be titled Extraordinary Accomplishments of the In-Space Production Applications Portfolio in 2024 and 2025. So go ahead and kick off the presentation.
Greetings to all interested in space development, and happy 25th anniversary to the International Space Station community. My name is Lynn Harper, and I support NASA's In-Space Production Applications portfolio, known as INSPA. My colleagues and I put this presentation together to share something new about in-space manufacturing. Game changers. These are microgravity-assisted applications that are delivering big impacts in very small packages at all levels of the organization of matter. These technologies are being produced in space for Earth markets and medicine by important new players who are developing low Earth orbit and industries of the future. Something happened by the end of 2024 that increased the importance of developing low Earth orbit. Microgravity delivered. Microgravity delivered on its 50-year promise of breakthrough science and important commercial and medical applications from space. Beginning in January 2024, world-leading researchers, innovators, and space payload developers were providing compelling evidence proved by demonstration on ISS and confirmed post-flight by independent experts. Microgravity processing significantly improved a wide range of high-value, high-tech, biotech, medtech materials and products with life-saving importance or wealth-generating potential, or both, at all levels of the organization of matter, from quantum to human. That's a big statement. In 2025, the story got better. Payloads. They're the people, the projects, and enterprises that pay for all space transportation and in-space services. They're the reason you're sending a person or object to space in the first place. While almost all of the media attention is on the launch vehicles and commercial space stations, in reality, payloads pay for everything, and it's time to pay close attention to what they can do. For more details, you'll have to listen to the other presenters and see the 20-minute version of this talk. But the summary of the following advances were achieved in payloads that varied from the size of a shoebox to about the size of a tall kitchen garbage can. But what they did within those small volumes changes the strategy for LEO development because the results were that good. Since January of 2024, exceptional results, important for superior applications on Earth, have been coming into the NASA INSPA and the ISS National Lab at an unprecedented rate. We called on other government agencies to help us interpret the findings and confirm the results, and they did. This slide shows the major areas where microgravity consistently delivers significantly better yields of disruptively superior products, important for life-saving advances, life-enhancing medical devices, and several high-tech industries. Any one of the top advances we saw would have been a cause for celebration. Together, they are literally game-changing, not just in space, but also on Earth. We let the data talk to us, and it told us something unignorable. When defects at the atomic and molecular level matter, microgravity often helps solve the problem better, cheaper, and faster than what can be accomplished on Earth. As more quality, yield, and performance data from microgravity came in, the story kept getting better. No one accomplishes spaceflight projects alone. It takes a village to enable successful enterprises in space, and it took a village to enable those reported here at the ISSRDC, and many more besides. The authors would like to recognize and thank all of the people and organizations listed below for informing this report. It is not a complete list, and we could not have done it without you. Very different futures are available to those who can thrive beyond Earth versus those whose resources and destinies are constrained to this world. Happy 25th anniversary to the first human settlement beyond Earth. What you did changed everything. And the more we look at the microgravity results being delivered daily from ISS, the story just keeps getting better.
All right. Welcome, Lynn. Thank you for that wonderful talk. I think we all appreciate a little bit more positivity in our lives nowadays, and that was a very uplifting talk. So while we wait for the chat to populate, I guess I'll go ahead and start. So you talked a lot about the results that have happened the past couple of years. I was wondering if you can expand a little bit on how you see results going forward as we, near the end of ISS, and how you see that impacting the transition to CLDs and other commercial space platforms.
So, first of all of the plans for deorbiting the ISS occurred before we knew the 2024 results. So one of the first things that we need to do is to identify how not to lose momentum for whatever plans that we make in LEO. That's why I said these are reshaping it, because literally we're looking at results that are so good that when defects at the atomic and molecular matter, when you need quality better than anything you can get on Earth, and when gravity has been masking important phenomena in the field, this is where microgravity can help. And it is in for very lucrative industries. Just the Keytruda results alone from 2019. They're looking at a $20 billion product because they saw a form of crystal they had never seen on Earth, even though they had been in the lab 10 years. Yeah. Yeah. So these are not small amounts of money. You just heard from Single Crystal Diamond a few minutes ago that they're looking at $200 million a year revenue as soon as they can get there up there often enough to get into the sweet spot of manufacturing. And we're seeing this time and time again in every one of the we have right now about 14 projects that we call Sagan class, because Carl Sagan said extraordinary claims require extraordinary evidence, and these are the groups that delivered both. And then we had them independently validated by third parties. So this is like nothing I've ever seen in my 40-year career working with microgravity payloads.
And I think some of these questions expand on that really well. So we have a question here from a commercial LEO perspective. What do you think are some good lessons learned for the commercial LEO developers? I think considering the experiments that you talked about and those hoping to fly their work on these new platforms.
So that's a great question. In fact, it's a central question. And here's why. When you send something to space and you're doing it as a commercial product or an important application, even if it's not profitable, if it's going to be used for a government purpose or something like that, where the quality matters even more than the price, then everything needs to work perfectly. Your launch needs to be right, your in-space services need to be right, and your return services need to be right as well. And so, I do this as a joke, but it's true. There's nobody on Earth that starts a precision experiment by shaking it for 7 minutes, and then saying, well, gee, let's turn that on and see if anything, is okay. So not only does the product have to be better than anything on Earth, but it needs to be so much better that it makes sense, business sense, to manufacture it in space. And for that, you don't get a pass on anything. In the early days of the space experimentation in bio on the space shuttle, we lost a lot of payloads before they even launched. So these are the results of people who have learned how to overcome all of those different steps and control the process end to end. And that's what CLDs are going to need to provide. Otherwise, they're not going to get the quality necessary to pay for the transportation and the other services. And that, by the way, is practice, practice, practice.
All right, well, thank you very much, Lynn. We're out of time. But as we said for the previous ones, feel free to continue these conversations in the chat and check out Lynn's full presentation on the website. So thank you again for your wonderful talk. And we will move on to our next talk by Paul Kuhl with Space Tango, Studio Precision Robotics for High Fidelity Microgravity Experimentation. Start off with the video.
Hi, my name is Paul Kuhl, and I'm the Director of Mechanical Engineering here at Space Tango. Welcome to the executive summary for Studio, Precision Robotics for High Fidelity Microgravity Experimentation. The next area of microgravity research demands more than legacy tools. It requires platforms built for constraint, scale, and autonomy. Right now, researchers face growing limits like launch access, crew time, and return capacity. Our CubeLab platforms have proven that they are valuable. They allow us to develop a wide range of automated systems for microgravity research and manufacturing, but they were never designed for the challenges that we're facing right now. Science today needs higher throughput, real-time insight, and adaptable protocols. So to achieve that at Space Tango, we have to reduce reliance on astronauts and increase automation and flexibility. That's exactly what Studio delivers, a reusable, autonomous platform built for the next generation of space research. So Studio is not just an upgrade over CubeLab, it's our answer to what comes next in orbital research. In this session, we'll talk about Studio's architecture, how its robotic capabilities apply directly to real scientific workflows. You'll see how Studio's tray-based design and precision robotics enable complex operations like fluid transfer, sampling, on-orbit imaging, all without any manual intervention. With interchangeable tools and sterile protocols, Studio can expand its utility across a wide range of scientific disciplines. The session will also explore operational concepts for both life sciences and physical sciences and show use cases where Studio makes the biggest impact, where we need dynamic control, repeatable conditions, and in situ analysis. Finally, we'll look at how reconfigurable platforms like Studio will change access models for research on orbit, making it possible for more research teams to conduct meaningful science as new destinations open up. On behalf of Space Tango, thank you. If you have any questions, please scan the QR code on the screen and connect with us.
Great, thanks, Paul. Welcome and thank you for your presentation.
Happy to be here.
All right, well, we already have a question in the Q&A, so we'll kick it off with that. What tools and capability are the main highlights of Studio?
So really, it's the next generation of our, on-orbit automated capabilities. We really wanted to maximize what we can do in space and minimizing the up mass, down mass. So, we really wanted to ensure that the science is the main focus. And so, with constraints nowadays, launches maybe being less frequent to ISS, the more mass that can be science, the better. And so Studio really just provides all of the autonomy, all of the things that your science would need already on orbit. And so we can maximize that up mass to being almost entirely the science. Unlike CubeLab, that is really specific job and it has all of that capability with it as it launches. We're making that all automated on orbit.
Okay, so did you design Studio to be still experiment specific but more versatile, or is it suitable to like multiple research areas at once? I know I heard like exchangeable heads and things like that.
Yeah, so really a very wide variety of experiments. So, it could be cell culture, physical sciences. We'll have the ability to control a robotic arm that will be able to use different end effectors. And then whatever your experiment needs, obviously we'll have a list of capabilities, but if the experiment works with that list of capabilities, then, we could do it.
Okay. Where are you at on your technology maturation timeline? Do you have a in-space demonstration planned out?
Yeah, so we have an in-space, our target is for the end of 2026 to have a demonstrator on ISS.
Okay.
So we're currently actively prototyping all the different devices. We are, our arm is switching end effectors and doing fluid protocols and things like that.
And we have another question in the chat here. Can you describe the inline capability to provide quality assurance for your payloads? For example, what kind of metadata, imagery, and sensors, et cetera, can you provide?
Yeah, so one of the big needs that researchers have had that we've seen is just getting more data on orbit. And so Studio provides microscopy, bright field, 3-channel fluorescence, and it can do that basically at any time. Because it's a robotic arm, we can manipulate the samples in different orientations and get really high quality microscopy data. We'll also have, all of the just environmental data, temperature, gas levels. We'll have visual positioning systems that will be able to track where your experiment is. So there'll be a lot of focus on kind of the regulatory things. We want to make this a clean, sterile environment where you can track where all of the different pieces of the automation have been, where it's been stored, where it was moved, what kind of pipette was used to transfer the fluid from well A to well B. So we're really thinking through replicating a ground lab as much as possible in space.
Yeah, I imagine all your CubeLab expertise and in-flight experience came in handy designing that. I guess I have one more question, and then we might be out of time. We'll see if anything else pops up in the Q&A. So what kind of temperature ranges can you all accommodate in there, and can you maintain those during transit?
Yeah, that's a great question. So Studio is intended to stay on orbit. But Studio offers a wide variety of temperatures. Like you said, with CubeLab, in a already a very small volume, we're able to control 4C all the way up to 37C, so fridge temperatures and incubation temperatures. So we have the same plan for Studio. We'll be able to control fridge temperatures up to incubation temperatures or higher if needed for a specific experiment. We'll be able to control also the CO2 levels in the incubation part of the Studio. As for transport up and down, Space Tango is developing products that'll be able to have that conditioned storage up and down, whether that's frozen all the way up to incubation temperatures. And we can also do soft stow solutions depending on the needs for the experiment.
Very great. Thank you. I think we all look forward to seeing more on Studio in the future.
Yeah, please check out the full presentation. We kind of go into a lot more detail on all the different systems for Studio. So it's an in-depth review.
All right, great. Thank you, Paul. We appreciate your time and your presentation.
Thank you.
And Paul, there's one more question in the chat. So if you want to just stay on for a couple minutes and answer that question directly in the chat, or just pose it as another question, I'm sure that person would appreciate it.
Yeah, no problem.
Thanks.
All right, thanks, Jim. So we'll move on to our next presentation. We have Atul Kumar with SpaceForge is going to present on a business case for developing PECVD, plasma enhanced chemical vapor deposition tool for deployment in orbit, enabling high-value semiconductor manufacturing in LEO. And we'll start with the presentation.
A very good day to all participants who are joining this virtual technical session at the ISSRDC 2025. I would like to thank you all for your interest in this presentation. Hi, my name is Atul Kumar. I'm from SpaceForge, and as you can guess from the title, the focus of this presentation will be on why we want to manufacture semiconductor materials in space, some of the challenges, and how we can potentially address them. Please note that this is a summary presentation that will focus on the key points, and I encourage all of you to download the full presentation for more details. This slide lists some of the reasons why we want to manufacture the semiconductor materials in space and potential applications of space-grown semiconductor materials. As a reminder, crystal growth in space has been demonstrated multiple times in the past. Several experiments, including those conducted on the International Space Station, have demonstrated significant improvements in the material properties of crystals grown in a microgravity environment. Continued improvements in the physical properties of these space-grown semiconductor materials will significantly boost their existing applications, and additionally, they will enable new applications. Some of the potential applications are listed on this slide. This slide lists some of the barriers to manufacturing semiconductor materials in space, and we will discuss these in the next few slides. In this slide, I have summarized 3 of the main challenges to manufacturing semiconductors in space and potential solutions. These 3 are related and involve access to space and return. Most of us are familiar with these, and I will not spend too much time on these in this summary presentation. The good news is that launch costs are coming down, and there are several companies working on orbital stations and platforms that can host the semiconductor payloads. In addition, we have companies working on reliable and cost-effective solutions for returning materials from space. Another big challenge in manufacturing semiconductors in space is the semiconductor material growth tool design complexity and constraints for in-space operation. Terrestrial semiconductor deposition and processing equipment design and manufacture is already complex. Designing and manufacturing a semiconductor tool that can be launched and operated in space is a major challenge. Some of these design challenges and constraints are listed on this slide. Successfully addressing these challenges require a fundamental shift in our approach to designing process equipment for space operations. Some of these innovations are coming online, and I highlight the first generation of our space-capable plasma-enhanced chemical vapor deposition tool that is currently on orbit and conducting tests. Let us now turn to the last challenge on our list, and that is the limited amount of material returned per mission at an extremely high cost compared to the terrestrially grown semiconductor substrates. While the space-grown semiconductors will be of extremely high quality, the cost of the material per unit weight would still be too high to justify use in many of the typical device applications. Instead of building devices directly on these semiconductor materials grown in space, we propose to use the high-quality materials as seed material for further terrestrial crystal boule growth. The resulting crystal boules can be further processed to produce several substrates for commercial use. The assumption is that the space-grown seed material will have the lowest defect density possible, and therefore the resulting semiconductor material grown on this seed will have superior properties as compared to the conventionally grown substrates. A schematic representation of this approach is shown on the figure on this slide. This hybrid space terrestrial semiconductor manufacturing model can result in substantially lower per substrate cost, which we think will justify use in several commercial applications. To summarize, manufacturing semiconductors in space is a challenging task, but there are solutions available that we can apply to address these challenges, and a combination of these will enable a pathway for commercial manufacture of semiconductors in space. Thank you for your time and interest, and I welcome any questions that you may have.
Welcome, Atul. Thank you for your presentation.
Thank you for having me here.
Absolutely. We already have some questions popping up in the Q&A. Let's see. I think Acme Materials grew silicon carbide wafers in space and got good results. Space Forge looking into this.
So for now, it's not a secret we are looking into diamond materials, but silicon carbide and gallium nitride are of materials of interest to us, and those are some of them that we'll be looking at down the line.
Okay. Do you have any demonstrations in the pipeline right now, and kind of what are
So
the...
there is one on orbit right now, the 4-star one was launched in June, and that's kind of our demonstration mission where we are testing a lot of these subsystems and hardware, and hopefully we'll be sharing some more data in the coming few weeks.
Okay, so that'll have return capability as well?
So the platform itself is designed for return, but unfortunately we could not secure the licenses for return. So even though we will be doing a technology demonstration on the return capability, the payload itself will not be coming back to Earth.
Okay. Well, so we wait for a few more questions to pop up here. There we go. What flight frequency is Space Force looking at?
So it's a limitation on the availability right now. And if we have our way, we would be launching almost every month if we could. And eventually, as we scale up, that could expand significantly more.
Okay, so you mean the availability of launches at this time, or?
So availability of launches, platforms, and also one of the things that I highlighted is the return capabilities that are currently severely limited.
Okay. And you said, we have a question there about your first flight. You said you already had your first flight in June.
So it is currently circling us right now. It's on orbit, and we are doing some system testings and getting a lot of interesting stuff back from it.
And we've got another question there. Any thoughts to flying some version of wake shield facility or something like that for ultra pure vacuum?
So that's a discussion that we are having right now in the future architectures. That could be something that we'll be looking into to improve the background gas levels. So yes, absolutely.
Very interesting. All right, we probably have time for 1 or 2 more questions if anything pops up in the chat. If not, I guess I can go ahead and ask another one.
Sure, please.
Okay. Yeah, so I guess have you thought any more about what things look like for Space Forge as commercial LEO destinations start to come online, and how do you all work together, and are there any synergies there?
Absolutely. Like, I mean, so again, like the reason like we built our own platform was just for the simple necessity. But as we have other orbital platforms and stations coming up, we'd love to partner with them. I think that there's a lot of synergy there, and hopefully that will give us a chance to expand our footprint onto different stations and platforms for operation in space.
Okay, yeah, like Lynn said, it takes a village, right?
Absolutely. Like, I mean, a lot of pieces of the puzzle have to fall in place at the same time for this to be like commercially successful. So absolutely, we look forward to all those partnerships.
Okay, great. Well, thank you for your time.
Thank you.
Has any more questions for Atul, feel free to message him in the chat. With that, we'll move on to our next presenter. Next, we have Jennifer Reed, founder of Helios Spectrum Consulting, with a talk titled From Concept to Commerce, Building Regulatory-Ready Infrastructure for In-Space Biotech Manufacturing. And here's the presentation.
Hello, I'm Jennifer Reed, founder of Helios Spectrum Consulting. My work sits at the intersection of space manufacturing and pharmaceutical regulation. Over time, I've seen that while technical progress in microgravity has been extraordinary, regulatory and quality planning are only more recently beginning to progress. Today, I'll share an integrated readiness framework to help align science, compliance, and commercialization, so that what begins as an experiment in orbit can successfully reach patients and markets on Earth. In-space biotech has moved well beyond proof of concept. Just look at the amazing things that Lynn Harper's presentation has shared. We've seen breakthroughs in crystallization, tissue models, and even drug development. NASA, startups, pharma, and investors are all leaning in. But the retirement of the ISS and NASA's evolving commercial LEO development strategy mean there's urgency. Private free flyers are coming online, and competition for access to orbit is increasing. This will be the critical moment to make sure we are building regulatory-ready infrastructure, as well as the continued amazing science and technical demonstrations. Here's the challenge. Microgravity's advantages often clash with terrestrial regulatory standards. Limited flight access and small sample sizes can raise the risk of unusable data or regulatory rejection. Too often, teams have had to prioritize their focus on technical milestones, and GMP, CMC, and quality planning have had to be set aside for future development. Right now, there's no shared framework that integrates technical, manufacturing, and marketing readiness. Stakeholders need tools to see the true path to production. One solution is an integrated readiness framework. It brings together three dimensions: technology readiness, market readiness, and manufacturing readiness. This acknowledges that de-risking isn't just about the science. It must also include compliance and operational planning. By combining these into a tiered model, we give stakeholders a structured way to track progress, align milestones, and build infrastructure that supports real commercialization, not just research. This framework matters because it enables better decisions. NASA program managers can use it to align projects with strategic goals. Commercial LEO developers can identify what infrastructure is really needed. Biotech startups can prioritize resources more effectively, and investors gain confidence that teams are addressing scale, compliance, and market pull. It reduces risk, builds a shared language across the ecosystem, and keeps us focused on the end goal, turning microgravity science into impact. To close, in-space biomanufacturing demands integrated frameworks that reflect technical, regulatory, and operational realities. By unifying technology readiness, market readiness, and manufacturing readiness levels, we move beyond siloed metrics to a holistic structure. This helps reduce mission risk, align regulatory strategy, and accelerate commercialization. Readiness must become a shared discipline because only then can we move from demonstration to deployment, from concept to commerce. Thank you very much.
All right, well, welcome, Jennifer. Thank you for your talk.
I was laughing at myself. It's so weird to hear yourself and all the nuances and technical stuff of reporting. So
Yeah, I understand.
happy to be here.
Yeah.
So happy. Thank you.
And Jim and I being the only faces on this
Yeah.
for 300 people. So, okay. While we wait for, oh, there's a question in the chat, so I'll start off with that. Is this biotechnology framework for commerce applicable outside of biotechnology?
Absolutely. And I'm glad that was the first question, because in general, if you're developing a product or doing manufacturing, all of these things apply. And so it's not just for in space. In space makes it more unique and gives you additional constraints to have to work with. But it would support manufacturing as a whole. Yes.
Okay. How
Does that
can,
make sense?
yeah. How can the ISS, and I assume that means, you know, NASA, the ISS National Lab, and all the folks involved in that community, help in developing the regulatory environment?
I think that's a great question. Thank you, Lynn. One of the things, one of my observations and goals of developing the readiness framework was to structure it so that it also followed along the INSPA work that's being done. So you'll see, you know, phase 01 is aligned with a phase 1 INSPA. And so I think embracing the idea that the main thing that's missing for you to have a complete look is to incorporate the manufacturing readiness now. So if you're going to build something in space, you hear all of even the kids in the STEM talking about the technical challenges to get their thing to work in space or to meet the constraint requirements. So when you add on top of that, anything that is regulated or has higher standards with regards to quality, everything that applies on Earth is going to apply in space as well. And so how do you meet those challenges? And so the goal is to stay informed at the beginning of what you're going to need to get there. And so that as you evolve, and again, the ways you implement quality and some of the regulatory stuff evolves as well as you mature with the market and the technical side of things, that you're able to make informed decisions, because it's a lot to keep in mind. And so if you have the big picture in front of you and you're assessing yourself at key milestones in all three areas, or as part of your proposal development, or if you're reviewing a proposal, Lynn, you might want to ask those questions. Are you thinking, how are you building quality in so that you can become, go online and produce?
Okay.
Mhm.
Yeah. On the biotech side, I think we've seen some of those conversations with the FDA start to happen.
Yeah, yes, for IFS. And that's great. And I want to plug some of the automated experiments that we've seen discussed today, because automation is probably going to be one of the things that, it's something that the pharma industry is incorporating, Pharma 4.0, advanced manufacturing. That's going to help you provide this inline quality and give the data to regulators to give you the metadata back to prove that I made the same thing every time and it was at this quality, and here's my evidence to do that.
So as these space-made products become more normalized, do you see any roadblocks through the regulatory process? And then
go ahead, finish your thought.
I was going to say, as a follow-up to that, I mean, the companies who are doing it now are kind of paving the way. So for the newer companies, I think the kind of crux of what you're doing is what can they do better as they start to help them further along the path, right?
Yeah.
Get faster.
Yeah. So roadblocks, forget regulatory. We're dealing with the government and government funding. And we've seen already that the commercial LEO developers, the acquisition planning has changed a couple of times. And so everybody's got to be agile and aware of all these changes. And what's a regulatory requirement today may not be tomorrow. They may change some of the rules. So you have to be prepared. And so I keep going back to this quality by design sort of aspect. We're most familiar in aerospace with like AS 9100 or ISO 9001. And so current good manufacturing practices are similar in that sense, but they're all geared towards protecting the patient. And so I think keeping those things in mind would be great. And then advice for the newer companies, it's not an art, but there is diligence associated with doing integrated readiness assessments. There's a lot of information in the pitch about each one individually. And so as these startup companies are getting funded, either through most likely SBIRs, you can request TABA, which is Technical and Business Advisory, maybe someone to come in, a consultant to help perform those for you, either as part of your proposal development or, assess along the way. And then be prepared, like Lynn was asking the right questions, try and assess yourself along the way. And then at the end, because your investors, that's one thing we haven't talked about yet, is investors want to see that you're building in the ability to get to scale and market. And so it really is this trifecta of goodness that helps support regulatory readiness as well.
All right, great. Thank you so much, Jennifer. There's a couple more questions in there that I think you already touched on a little bit, but feel free to answer those in the chat.
Yep, will do. And happy to talk to anyone, if you want to learn more or you want help setting something like that up. So it's fun. I love it. Thanks for the opportunity.
All right. Thanks again for your talk.
Thank you.
All right. We have one more talk for this session. Our next speaker is Partha Dutta, United Semiconductors. The presentation is titled Yield Enhancement of Device-Grade Semi-Metal Semiconductor Composites via Reduced Gravity Manufacturing Process.
And I'm just going to say, Partha's coming on. I'm not sure if the audio quite worked on his slides. So Marta from our team, if you can just start the slides, and Partha, if you need to talk to them and the audio doesn't work, please do.
Yep. Thank you very much, and sorry about the inconvenience in not getting the audio to work on my slides. So I'm Partha Dutta. I'll be presenting the summary of our very interesting and very significant Mission 1 on the ISS earlier this year. And this is on a new class of materials. We call it semi-metal semiconductor composites. And I'll share some of the initial results, which are exciting. The investigation is still going on with these materials and device fabrication. But I like to also acknowledge the team, the core team who contributed to this, the work here, and their names are listed here. So let's move on to the next slide. So the agenda is pretty straightforward. I'll quickly introduce what these materials are, and then the Mission 1 results, which are significant, and the Mission 2, which just launched a week ago. What are the objectives of Mission 2? Next slide. So Mission 1 happened between December 2024 and February 2025 at the ISS in the MSG glove box in the furnace called the SUPSA furnace under the conditions of crystal growth where semiconductor crystals have been grown in the past 25 years in ISS in this furnace. And this was the first of its kind material that was grown, and then the payload configuration was new, which is basically targeted for large-scale commercialization going forward. Next slide. So this is the hardware that we had sent to the ISS, and when we got back the hardware with the crystal that is grown inside the ampule that you can see here, we did all the analysis, and this was the first successful demonstration of a hardware that we have developed in our company. And this is kind of the prototype of how commercial scale, crystal growth for semiconductors would take place. And so it was very good to see that the hardware operated successfully in our experiments in ISS under microgravity, and it returned safely without any issues. Next slide. Then we started to dig deeper into the hardware, and this is the crystal that was regrown. Part of the crystal was remelted and regrown in the MSG glove box in the subsub furnace. And we tried to unravel all the mysteries and the significant things that we learned through this mission one. One of them is shown on this slide. We can see the solid liquid interface, which is clearly seen and highlighted here. And to our surprise, that the predictions that we had on the crystal and the location of the solid liquid interface was within like a millimeter or two from where we expected it is going to be happening. So that shows that the crystal growth conditions that we had developed terrestrially for the microgravity experiments were precise enough, and that provides a strong background for scaling up these kind of materials in space going forward. Next slide. This is the third-party validation courtesy NIST, these pictures, and this summarizes the significant differences in terrestrial crystals that were grown under same conditions in the ground control system at Redwire, in the subsub furnace at Redwire, and then the crystal that was grown in ISS. And I don't have to really talk more. You can see the differences in the morphology of the crystals that was grown in terrestrially and the space. And the key thing here I would like to highlight is that the distribution of the microstructure, which is the semi-metal needles, they are homogeneously distributed in the space-grown crystals, and the size distributions were very different. And this directly translates into a device yield of improvement more than 10x, and that's something very, very significant. This material has been used commercially for many applications for the last 60 years. And this is the first time we are seeing such high improvement in device yield from space-grown materials. Next slide. And this is another one which talks about performance. So this is again a third-party validation of a device fabricated, identical device fabricated using a terrestrial material and a space-grown material. And the magnetic gain that you see here, which is the figure of merit, has improved 2x. Again, I like to highlight that these devices are extremely mature devices in the semiconductor industry. And for the last 60 years, the gain is locked between 8 to 10. And this is the first time we see that the gain has significantly improved by a factor of 2x in the space-grown material with the mission one. Next slide. So going forward, we were ready for mission two as soon as we saw these significantly encouraging results. And so the mission two launched on September 14th with the NG-23 resupply mission. And these pictures shows all the people who contributed towards developing the payload, and it was done at a very rapid turnaround time in our company within a month's time. And so that's at ISS right now. And next slide. The objectives of mission two, based on the lessons that we learned in mission one, the objectives are two-fold. One is we want to reduce the crystal growth production time, the cycle time by 25 to 35%. That will actually lead to development of larger volume of materials that we can create going forward. And then the second one is to really look at the batch-to-batch repeatability for identical crystal growth conditions in microgravity. So this time around, we had 6 flight ampules that we have launched. Next slide. So in summary, we have seen or demonstrated the yield improvement in semiconductor type devices for the first time in space-grown crystals. We have shown that the device yield improved by 10x compared to the terrestrial counterpart, and a figure of merit improved by 2x already in space-grown crystal. We also saw a lot of other interesting features which are significant for large-scale crystal growth in space. One of them was actually a container-free growth feature, which not only provides uniform, homogeneous nucleation for crystals, but also for lower defect density. And we also saw in my long presentation that we have online, you can see some of the novel features in these crystals, which will enable new electronic device technologies in the semiconductor industry. Next slide. I'd like to actually acknowledge a few key people here. Kevin Engelbert, who has been a champion on this INSPA portfolio, who is the INSPA portfolio manager, has been the champion for this program. And thanks to Kevin for all the enthusiasm he brings to the table, due to which I think we have been very successful. Dr. Martin Bowles was our technical monitor at NASA MSFG, and he has experience with microgravity crystal growth for the last 25 years. Dr. Hua Su, who is our current technical monitor at NASA MSFG, and Ms. Heidi Paris, who was really instrumental in getting the payloads for Mission 1, installed and developed, and helped us get into ISS as soon as we wanted. And also the implementation partner CSS and Redwire folks, and our partner Axiom Space. Thank you very much.
All right. Thank you, Partha. I think it's safe to say that you have some of those extraordinary results that Lynn mentioned previously.
Thank
So
you.
give it a second. I imagine we'll probably have quite a few questions pop up in the Q&A. And I guess I can start off with a quick one before that happens. I saw on your last slide, you mentioned some interesting behavior that was maybe unexpected. Can you expand on that a little bit, and maybe if you plan to leverage that going forward?
Absolutely, absolutely. Yeah. So we saw features. First of all, we had a hypothesis that the microstructure is going to be uniform, aligned, so that we can make larger volume of devices from them. But we also saw some interesting features on the length scale of these microstructures, which suddenly opened up new device architectures that we can start to envision. For example, we saw extremely long semi-metal needles, which actually can be used for FinFETs. And we were not planning to actually make FinFETs with these materials. We were trying to make magnetic sensors, but what we saw was so encouraging that in Mission 2, we are going to be leveraging those crystal growth conditions under which we saw those large needles, and exploit them for high-speed transistors, ultra-high-speed, ultra-low power transistors, and things like that. They'll actually enable these materials into semiconductor fab in a rapid turnaround time for transitioning from the silicon-based devices to beyond silicon devices with semi-metals. That's one of the examples.
Okay, I think you actually covered one of the questions that popped up. Does the quality of the space results open up new applications you hadn't considered? And I think you just answered that as yes.
Yes.
Have you looked at growing amorphous metals or metallic glasses in space?
That's something in our plans. If anybody's interested in any specific material system, we'd like to actually know that. We have certain class of glasses that we are planning to manufacture in the near future. And so because we saw this highly homogeneous nucleation sites, that's actually in one of the long presentation, I have that picture where we show nucleation of crystals in space, extremely homogeneous at the liquid solid interface shape, and very different from what we see terrestrially because of sedimentation and buoyancy and things like that. So we can actually leverage that for amorphous materials very well as multi-crystalline materials where the grain size and the morphology and the composition phase really matters. So to answer your question, yes.
Okay. Next question, how do the magnetic properties you obtained from space samples compare to anything available in the commercial market on the ground?
So I showed the graph. We saw a 2x improvement, which is a very, very big quantum leap in performance, because these devices, people have worked on this device architecture for the last 60 years. So these are not new, and they have not been able to really go beyond the 8 to 10 figure of merit, which is the magnetic gain. And that's because the randomness of the microstructure in terrestrial grown crystals, but with the space grown crystals with aligned morphology, we had to do nothing except fabricate the same device structure that we do terrestrially. Again, we have a lot of database on these devices we do for our customers, DoD customers, terrestrially, and we saw a gain of 14 to 16 in one of the graphs I showed. And that's actually a significant jump. And we're not even actually gone into device designs which are more suitable for microgravity materials. So we are working on that as we speak. We expect that the device performance will improve further, but at the least we have a gain of 2x, which is significant.
Okay. And I'll ask one question myself, and then we'll go ahead and close it out for the day. But my question is, do you plan to disseminate your results? I think, nowadays with all the things going on politically and otherwise, that the more positive results we can get out to the community, the better.
Absolutely. We will have not just press releases, but we are securing a lot of IP on this thing. And that's one of the reasons. And we are learning a lot of new things through third-party validation as we speak. So we are gathering all of those things. At some point, we are also going to actually have peer-reviewed publications, high-quality publications with our third-party validation partners like NIST and the universities. So that actually the scientific community can see all of these results. And at the same time, we'll be very active in doing a lot of press releases and also like creating new partnerships for in-space manufacturing. And you're going to see those in the coming weeks and months through press releases.
All right. Thank you very much, Partha. We appreciate your presentation and your amazing results.
Thank you very much for the opportunity.
Yep. We look forward to hearing about mission 2.
Thank you.
All right. So with that, that concludes this session. So thank you all attendees and authors for your time and your interest in the space industry as a whole. Just a reminder that all these presentations will be available online. Webinars are being recorded and will also be available. Our next session of the day will be next at 3:30 p.m. Eastern Time, commercial and non-governmental use. Jim, do you have any final words?
No, thanks everybody for being here. We're going to try something. I know Jennifer Reed had some additional questions, so I'm bringing her back in as a panelist to see if she can see them so she can answer them. If not, I'll figure out a way to get them to her so they can be answered.